When most managers want to optimize a process with multiple variables, they use the traditional one factor at a time method. They change one thing, keep the rest constant, and measure the result. It sounds logical, but mathematically, it is an absolute disaster. It completely misses how variables interact with each other, wastes massive amounts of time, and costs a fortune. In the improve phase of Six Sigma, we do things differently. We use design of experiments, or DoE, to deliberately change multiple inputs simultaneously. This allows us to calculate the exact interaction effects between variables with a minimal number of test runs.
Section 1. The optimization disaster.
Okay, let's dive right into this explainer. The fundamental flaw in modern business is treating complex operations like a simple linear equation. If you genuinely believe that tweaking just one machine setting in a total vacuum will magically solve your production issues, well, your business is literally bleeding money. Think about the traditional OFAT approach, one factor at a time. It's kind of what you do when you just don't know any better. You change the temperature, you measure the result. You change the speed, you measure again. It operates under this incredibly dangerous illusion that variables don't affect one another. But then we have our ultimate operational weapon, design of experiments, or DoE. Instead of guessing, DoE tests multiple inputs simultaneously. It's a master tactical approach that systematically reveals the hidden variables and the actual mathematical realities of your process. To achieve true operational excellence, we absolutely have to abandon OFAT and embrace the precision of DoE.
Section 2. The core of DoE and interaction effects.
So what are the underlying mechanics here, and why exactly are interaction effects the absolute secret to perfect processes? Well, a design of experiments isn't just a random series of trials. No, it's a highly structured mathematical method. In Six Sigma, we say that your output, your Y, is a direct function of your inputs, your X's. Instead of testing literally thousands of random, messy combinations, DoE systematically maps out this entire relationship to find the absolute ultimate operational recipe. We are totally replacing guesswork with predictive science. And how exactly do we pull this off? It all comes down to a factorial design matrix. Think about the extremes, the high, or +1 settings, and the low, or -1 settings for each factor. Instead of testing every single microscopic adjustment in between, a full or fractional factorial DoE strictly uses these boundary limits. By running these specific high and low combinations, we can mathematically map out literally every possibility within that boundary, and we do it without the immense, expensive waste of trial and error. It is ruthlessly efficient.
But here is where the magic really happens, the interaction effect. I want to stress this concept heavily, because this is exactly where OFAT completely falls apart. An interaction effect occurs when the impact of one factor on your output depends heavily on the specific setting of another factor. Think of it like a tactical strike. Imagine a specific packaging glue. Now that glue might only hold at a high conveyor speed if the temperature is also set to high. If you're testing speed and temperature completely separately, you will never, ever find that perfect combination. But DoE, it finds it every single time.
Section 3. Deconstructing resolution and confounding.
Now, in the real world, running massive tests gets really expensive really fast. We obviously want to save money by running fewer tests, which is why we use what's called a fractional factorial design. But cutting corners introduces a major risk, confounding. In Dutch Six Sigma literature, there's a great word for this. It's described as verstringeling, an entanglement. When you reduce the total number of test runs, your data gets tangled up. The effects mix together, making it mathematically impossible to separate the true impact of a main factor from a combined interaction effect. Because of this entanglement, we have to classify our experiments by resolution. Think of this like a threat assessment. First, you have resolution 3. This is highly risky. In a resolution 3 design, your main effects are hopelessly confounded with two-factor interactions. You might see a huge spike in quality, but you won't actually know if it's because of factor A or a sneaky combination of factors B and C. It's really only good for quick initial screening. Next, we have resolution 4. It's definitely safer, but your two-factor interactions are still totally mixed up with each other. Finally, we arrive at resolution 5. This is the flawless gold standard. The main effects are perfectly clear, and the interactions are perfectly clear from each other. There is absolutely no dangerous confounding here.
Section 4. The BlueprintRM case study. Let's ground all this advanced theory into a high-stakes, real-world scenario with our premium e-commerce logistics partner, BlueprintRM. Here are the parameters of our operational heist. The black belt in charge has a very clear goal, our why: maximize the premium unboxing experience and minimize any package damage.
To pull this off, they're looking at three main input factors. X1 is the sealing temperature, low versus high. X2 is the conveyor belt speed, slow versus fast. And X3 is the cushioning material, standard paper versus a premium foam. The team needs to absolutely optimize this delivery process, but without running endless, incredibly expensive trial and error weeks. So they smartly set up a fractional factorial DoE.
But here is the critical dilemma they face. Do you go cheap or do you go accurate? Will choosing a cheaper Resolution 3 design save the budget, or will it completely destroy the premium brand? Think about it. If we blindly pick a Resolution 3 design just to save a few dollars, and suddenly we see a massive spike in quality, we're essentially flying blind. We won't know for sure if that quality came from the expensive premium foam, or if it was actually a hidden interaction between the sealing temperature and the conveyor speed. So a tough executive decision has to be made. With a Resolution 3 design, the true cause of your success remains mathematically hidden, and you simply can't scale what you don't understand. To properly protect this high-end brand, the Black Belt deploys the Resolution V design. We demand perfect clarity. We absolutely must be able to cleanly separate the main effects from the interactions. No dangerous confounding is allowed on a project like this. And the payoff? It is spectacular. Because they used the gold standard Resolution V, the mathematical model revealed a massive, hidden truth. The high sealing temperature works absolute miracles for the packaging, but only when the conveyor speed is set to fast. If they had used the old OFAT method, they literally never would have found this relationship. The DoE flawlessly isolated the exact interaction effect, handing the operations team the perfect, math-backed blueprint for success.
Section 5. The strategic value. Understanding the math is really only half the battle. Applying it to drive total business dominance is the ultimate goal, translating those statistics into a literal boardroom superpower. Deploying DoE with the correct resolution does three huge things for you. First, it completely turns process improvement from an art into a predictive science. Second, it entirely eliminates those expensive, wasteful guessing games. And third, it guarantees maximum quality at the absolute lowest cost. A Six Sigma black belt armed with this data doesn't walk into a boardroom with a guess, they walk in presenting irrefutable, mathematically guaranteed operational settings. So, the major takeaway you should burn into your mind is this. Design of experiments is not just a statistical tool. It is the ultimate mathematical weapon for operational excellence. It asserts absolute dominance over basic trial and error, turning complex, chaotic operational variables into a streamlined, proven path to perfection. Once you truly master the DoE matrix, there is no process you cannot optimize.
So the very next time you face a massive operational failure, ask yourself, are you going to keep guessing with one variable at a time, or are you ready to engineer absolute certainty for education and entertainment?